Hi everyone, thank you so much for joining us for today for the next installment in the UEFI 2021 Virtual Plug Fest. We'll get started in just a moment here. Thank you. Hi everyone, thanks so much for joining us for Traceable Firmware Bill of Materials Overview webinar as part of the UEFI 2021 Virtual Plug Fest. I wanted to take a minute here to introduce our presenters. So we have Amy Nelson, who is a distinguished member of the technical staff in the Software Engineering and Dell's Modern Computing Solutions Group. We also have Jaewin Yao, who's a principal engineer in the Intel Software and Advanced Technology Group, and Vincent Zimmer, who's a senior principal engineer in the Intel Software and Advanced Technology Group. And from there, I'll go ahead and pass it off to the presenters.
Good morning, good evening, everyone. I'm Amy Nelson, and today we're going to give you a little bit of background on firmware bills of materials, and we'll actually talk through what a firmware bill of material is and why we need one. And then we'll give you some examples and show you kind of how those things play in the real world and provide at the end a summary and call to action. So to start, some of you probably, maybe all of you, have heard about supply chain security. It's been much in the news over the last few years, and I'm sure that all of you are aware, particularly in the process of building and deploying firmware, we have a lot of places in the supply chain where it's possible for an attacker to install themselves, intercept something, or end up subverting the processes that we need to enable secure delivery of code with some level of integrity. So, current practice today largely relies on contractual arrangements and essentially trust. And what that results in is, in the event of, um, a piece of malware or subversion of the process, it's very difficult to detect it. And what we really need is a way to cryptographically um, verify the authenticity of hardware and firmware without only having the option of relying on um, contractual arrangements. So, what is a software bill of materials? This is a term of art that's been around um, for quite a while, and in general, it leverages the traditional bill of material terminology, which is a list of the raw materials, subassemblies, intermediate assemblies, subcomponents, parts, and the quantities of each needed to manufacture an end product. In the construct of software, a software bill of materials is the uh, basically the third-party dependencies, including any transitive dependencies that are built into a software package. So there are several ways of doing software bill of material today. There's the software package data exchange, which is standardized by ISO, and there are open source tools and examples for that. There is SWID tags, and this is also an ISO standard, but there's a NIST document here as well. And there are tools available for generating SWID tags. There's the Common Platform Enumeration, or CPE, methodology and tool set, and it's used to describe applications, OSs, and hardware today. which is standardized by NIST. And then there's the Cyclone DX software bill of materials, and that is actually used quite a bit today if you're doing any third-party dependency scanning. Um, most likely, Cyclone DX is used in that process. So when we talk about firmware, how many different types of firmware exist in a typical PC platform or desktop platform today? We have the UEFI firmware. We have management engine firmware. We have CPU microcode. We've got BIOS ACMs. We've got SNIT ACMs. We've got BMCs. We've got network controller firmware. We've got PXE option ROMs. We've got RST OROMs. We've got video OROMs. We've got memory code. We have NVMe code. We've got PCIe device code, and the list continues. So specifically around supply chain issues in firmware, researchers have been starting to poke on this. This is a talk that was given at Black Hat this year. It is not the only one. And this is one of the reasons why we need to start focusing on the supply chain for firmware, not just the supply chain for software and hardware. So if we look at the existing technology that's available today, there is an open source tool that's been released by the US government, and it was initially released to validate TCG platform certificates, but that has recently been updated to support reference integrity measurements for firmware. It's the HERS tool, or Host Integrity at Runtime and Startup. They recently released version 2.0, which added support for the PC client reference integrity manifest specification from TCG. And what it does is it compares the set of measurements that it receives from the TPM that have been provisioned or have been made in the boot process by the BIOS against a reference integrity manifest provided by the manufacturer of the system or the manufacturer, the OEM of the BIOS. So when we talk about attestation for firmware, what are we actually trying to do? So we have all these firmware components that we talked about a few slides ago. And as the BIOS boots up, it's going to extend that stuff into the TPM PCRs. And it's going to produce an event log. And one of the things that we're working on now within TCG is actually producing a specification to comprehend more of the SPDM stuff, for instance. An appraiser will actually take the information from the TPM PCRs and it will compare it with something that comes from an endorser, say a platform certificate, and maybe the same entity in the supply chain provides the reference measurements, and there's multiple formats of those things today. And it compares what it sees from the TPM versus the references that it gets, the endorsements it gets from the manufacturer of the platform and various other endorsers. And it looks at the appraisal policy of the owner and it produces a result to the entity and the environment that is saying that is asking for this appraisal. So in this particular instantiation, the system firmware is the lead attester, meaning that all of the measurements are aggregated through the system firmware, which populates the results in the TPM. But there are some gaps today. BIOS is largely measured as a chunk, and maybe those chunks are separated into firmware volumes, but it's still considered a monolithic entity at the lowest level. So how do you know what components are embedded within the BIOS, and how do you know what those specific components are? Right now, basically BIOS measures itself and the things that it contains or the things that it can see. But how do we know about how do we understand the firmware that's actually embedded in each of the devices? So the way we get there is by the addition of or the definition of a firmware bill of materials. So a firmware bill of materials is a list of all the firmware components, their hashes, and class-related information for them, which are embedded or attached to the system motherboard and play different roles during system boot and runtime usage. There are several sets of specifications and standards which are available today. There's the draft NIST SP 800-155 BIOS integrity measurement specification or special publication. TCG published earlier this year the TCG PC Client Firmware Integrity Measurement specification and also the TCG PC Client Reference Integrity Measurement information model. And we have, and I'm sure many of you are familiar with the TCG PC Client Platform Firmware Profile. There also exists some IETF standards. There's a standard for a concise SWID tag and a COMID. So how do we go from there to the actual firmware BOM? And here I will hand it over to Jay Wen.
Okay, thank you, Amy. So since Amy gave a brief introduction on this firmware bill concept, now let's discuss the detail of the firmware bill of the materials. First, let's see what there's two class of firmwares in our definition. So for type 1 firmware means the firmware loaded and executed in the host environment. Host environment here means the general purpose CPU on the motherboard. The type 2 firmware is loaded or executed not in host environment. For example, a management engine firmware, BMC firmware, etc. Let's take a look at the detail. We have also give a subtype of this firmware classification. For the type 1A firmware, it is located in the system flash part and is executed by the host CPU. For example, the BIOS, Intel FSP binary, and CPU microcode, etc. We define the type 1B firmware. It is located in the peripheral device, but it is still executed by the host CPU. The example includes the PCI option ROM or NIC PXE firmware, etc. The type 2A means it is located in non-host part while executed in the non-host processor. The example are the BMC EC for embedded controller, Intel CSME or PFR firmware. They can interact with the host CPU. The last one is type 2B. It's in the peripheral device and executed inside of the peripheral device. For example, the network interface card, NVMe storage, NVDM storage, graphic card, etc. We give this classification because there might be different strategies to collect information for those type of firmwares. By design, the system firmware should load and measure all the type 1 firmware. Take static root of trust for measurement as example. The Intel authenticated code module loads and measures the BIOS initial boot block, which is known as the PI firmware volume. Then the PI firmware volume loads and measures the DXE firmware. Then the DXE firmware loads and measures the PCI option ROM and the OS loader. Ideally, each firmware component should have one or more dedicated entry in the event log, especially the one from different vendor, so people can know what the information is that. And then the system firmware itself may be measured or verified by the platform root of trust component, and we will discuss more in the type 2 firmware. This figure shows the current status. System firmware records the firmware information and PCI option ROM to TPM PCR and TCG event log. Later, a verifier can get those runtime information and perform the platform attestation. Then the verifier can get the platform certificate and the system firmware RIM and compare the information based upon the verification policy. However, there's some information not there. For example, the verifier may want to know what exactly system firmware includes. For example, which microcode or which FSP binary, etc. Maybe a platform just put all microcode in a big firmware volume and measure them together, so the verifier don't know the detail of microcode. The FSP binary are reported as a normal OEM firmware volume. The verifier doesn't know it is FSP or whether it is from Intel or not. The verifier might not know device option ROM information, which is challenge because the card can be plugged by the end user or something. The system firmware RIM might not have the device option ROM information at the manufacture time. A better solution we think today is to allow each component have its own event log entry and its own RIM. For example, a FSP binary has its dedicated event log, so the verifier knows this event log entry is for FSP. A dedicated FSP RIM is published to revert by the system firmware RIM. As such, the verifier can get the FSP event log and compare with them with the FSP RIM to know if it's the latest FSP binary published by Intel. For the Type 1A firmware, FSP is just one example. Actually, any third-party firmware component can use this similar mechanism. For example, a third-party onboard option ROM was usually included in the DXC firmware volume. The verifier has no chance to know the onboard option ROM information. We should have a dedicated event log entry for the third-party onboard ROM. Then the device vendor can create a RIM for this option ROM, and the platform vendor may reuse this RIM or create an update RIM if they made some modification. The rule is applicable for the Type 1B firmware as well. The option ROM or the PCL card should have a dedicated RIM to describe this information. The verifier needs to collect all related RIM to know the detail of the platform and track if each component is the latest one. Now let's take a look at the Type 2 firmware. Type 2 firmware doesn't run in the host environment, so the system firmware cannot load it. The system firmware may still want to collect information so that the verifier can have one place to know all firmware. Please aware that in some platforms it could be more complicated. A system firmware might not have access to some of the device root of trust directly, but it may get the Type 2 firmware measurement from other root of trust source, such as a platform root of trust. Here is the today's status on the Type 2 firmware. A system may have a platform root of trust, and the platform root of trust verify the non-host firmware and the system firmware. For example, the Intel PFR will verify the CSME and the BIOS. Then the system firmware collected measurement from the non-host firmware. For example, the BIOS can get a measurement from CSME and extend to PCR and event log. Similar to Type 1 firmware, the verifier can get the PCR and event log and consult the platform certificate and the RIM. However, today the Type 2 non-host firmware measurement is not standardized. The verifier does not understand those non-host firmware. And for the for the Type 2 device firmware, some of them may be verified by the platform root of trust. However, not all device firmware is handled by the platform root of trust. As such, many Type 2B device firmware is even not recorded. The verifier has no idea on what those devices are on a system. Here is the final picture on what we can do for Type 2 firmware. At the platform initialization, the platform root of trust may validate non-host firmware and system firmware. Later, as system firmware use SPDM protocol to communicate with the Type 1A non-host firmware or Type 2A non-host firmware or Type 2B device firmware to collect the measurement and record those information to PCI or event log. The SPDM protocol is the standard for the DMTF organization. The benefit of using SPDM protocol is that the measurement format is standardized. We can have a generic verifier to pass the SPDM-based measurement information. As that if we standardize that in TCG PFP spec as well, we can get that from TCG event log. Now the verifier can get the platform certificate, which point to the non-host firmware RIM and the system firmware RIM. The verifier can also get the device RIM information, it could point it by the platform RIM or a standard RIM. Finally, the verifier can compare the SPDM information, the TCG event log, with the device RIM or non-host firmware. And this is the final picture we think the platform should be. Now let's see some real example. Let Vincent Zimmer to introduce that and show how we do that in the Type 1 firmware.
Hey, thanks, Jiwon. So yeah, I think Amy gave a great overview of the ecosystem, some of the standards and business drivers behind this. Jiwon has framed up some of the infrastructure and schematically how the flows work. So I'm going to spend a couple minutes talking about an embodiment of this for the Type 1 or sort of the host firmware. And specifically, I'm going to talk about an example of Type 1 firmware based upon the Intel Firmware Support Package. So the audience may or may not know the Intel Firmware Support Package, or FSP, is a well-defined binary object that runs on the host CPU that's responsible for some basic initialization, including the memory controller, system fabric, but it's really scoped to the system on a chip. So the FSP itself doesn't have knowledge about the board information or other vendor features. So it's intended to really be a binary that can ship from the manufacturer of the system on a chip, in this case Intel, that the original equipment manufacturer can integrate into their BIOS. And to that end, really, we want to have it such that the OEM BIOS shouldn't have to modify it. It should drop in. But given that model, it kind of poses a couple of challenges or questions. Specifically, if Intel is publishing this binary, how does the OEM BIOS or other parties know that it's the genuine FSP? Is it the provenance is from Intel? And even if you know the provenance, what is the version of it? Because there may be a variety of them. So for example, even today, you could go to github.com/intel/FSP, and you'll see a plurality of FSP binaries posted there for different client and server. So again, this Type 1 firmware is any firmware that runs on the host. The FSP is just one element, but given that it advised to be a well-defined binary, how would it exist in this world of, you know, firmware bills of materials and higher fidelities supply chain. So sort of taking the FSP and some of the infrastructure Amy and Jiwon described, we'll going to discuss the next couple pages both the production and consumption of this infrastructure in the context of the Intel FSP. So in the lower left, we cite a document that you can find on at the bottom of intel.com/FSP called the FSP 2.x measurement and attestation document. So the way the FSP is deployed, it's a well-defined binary, but it needs some explication of how to interact with it. And to that end, there's something called a FSP EAS or external architecture spec. Right now it's 2.3. So in the context of these 2.x specifications, this document describes how to create and consume measurements around the FSP. And so the first part is the production of the reference integrity manifest. So this is sort of the offline creation process. And in fact, Jiwon has even created some tools referenced in that document to actually to create these RIMs. And long term, we'd actually like to have them posted on the GitHub site next to the respective FSP binaries. And so what is in them? So you heard about this RIM and software ID tags. And so the idea here is to essentially have a base RIM that describes this overall object called the FSP. It can give you what the format type, a unique tag ID, and then if you'll notice the name here is for a client FSP, the Amber Lake FSP bin. And then given that the FSP itself is with the 2.x, 2.3 is decomposed to several binary objects. There's one called FSPT for temp RAM init, FSPM for memory init, and an FSPS for silicon initialization. The RIM would then describe the identity and most importantly the expected hashes or digests of those components. So again, the workflow here is a production and a consumption of this type of information, and this is the production. So the manufacturer, the producer, the FSP creates this document saying this is the expected measurement information you should look for. And so now you're in the field. You have you're booting your firmware. The OEM has integrated the FSP. How do you assess what the provenance or the identity of that specific FSP in your system? And that's where this augmentation of the measured boot happens. And so we provided a example code that could be used in EDK2 that actually generates the event logs described in the TCG specifications and the prior slides 2.x measurement spec. And so again, the TCG event log already has a plurality of measurements for other host-based objects, but now there'll be an inclusion when you activate these type 1 measurements, live digests of the FSPT M&S. And so these are actually sampled directly from the SPI NOR flash for that running system. So the former slide was offline creation of the expected measurements, put them in the RIM. This slide is an actual system booting, generating a TCG event log in host memory. And then this slide is kind of the fusion of the two. So here's the system architecture document Jiwon showed earlier with the system firmware, the event log, and then the platform certificates and the RIMs. And this all sort of comes together by the verifier actually looking at the event log for this system under evaluation. There'll be some live measurements. And then the verifier can go grab the RIMs, and see, hey, does the manufacturer's expected digests for these components match what I'm actually seeing on the system? So this is kind of putting for type 1 this technology into play. The manufacturer again publishes the RIMs. The system manufacturer integrates code to create the measurements, and then the verifier now has an opportunity to compare the manufacturer's expected results with the system under test. So this is the embodiment of this this flow, and again, the collateral to create the RIMs, sample code to integrate into your host firmware is all public. And then again, we have a lot of examples of FSPs already and platforms that can build their solution based on FSPs today. So this is really an evolutionary approach to some existing infrastructure. But that's not the end of the story. So again, measurements and adding more track traceability and fidelity to measured boot is a great thing. But from a software supply chain, there are an extant body of binary objects, namely EFI executables in the ecosystem, that really having some traceability would be a nice thing. And so Amy mentioned the COSWID, the software ID, the compact software ID, NIST standards, the IETF drafts. So Richard Hughes in the LVFS project has created some tooling to actually ease integration of this into UEFI image creation and distribution. Specifically, he has a Python tool that you can run that'll actually take some of the this metadata about the image, summary, revision, etc., things that you can't easily derive from our existing PE-COF executables, and using this tool actually append a new section with this software bill of materials information, or a COSWID. And so Richard, presented some of this at the open source firmware conference last week, talked about the easy use, how this can be integrated into a build process, how services like LVFS will actually collect this type of information. So in addition to the great work that the Trusted Computing Group and DNTF and others are doing about these higher fidelity measurements, this is another way to add to the EFI ecosystem some additional traceability for type 1 firmware. Again, this is the type of firmware running on the host that we have a pretty evolved, mature ecosystem that we're evolving. But the next challenge really is building this out also for the type 2 firmware, as Jiwon mentioned. And to that end, I think I'm going to hand back to the world's expert on this area right now, which is Jiwon Yao, to give some examples of the type 2 firmware and work going on here.
Okay, thank you, Vincent. Here I will continue the discussion on this type 2 firmware, which is the device firmware. So a device may at least include one immutable ROM or a mutable firmware running on the device. A PCI device may also include a PCI option ROM, which runs as a BIOS driver in the system boot environment. If the device is active and used by the BIOS, such as a graphic device or a storage device or network device, then the device firmware and the PCI option are involved in the firmware boot process. Now the question comes to us is, how do we know the device firmware information which is involved in the boot, and how do we know the device option ROM information? In this figure, I showed a fake device RIM. The device RIM in the IETF CORIM format. It includes some vendor information, device mode, device ID, tag creator, etc. In the manufacturer phase, the device vendor creates the reference tag to manifest for the the device. For example, the device option role may use a code suite format and provide a digest, like EEE, which is a digest of the option ROM. And the device firmware may use a commit format. Here we show the three firmware measurement. Its digest is A, B, 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 and C, C, C. And the device vendor may publish this RIM information on the web. Then note that this is just a very simple example. A real base RIM may be much more complicated because the device may want to describe the precise layout for its internal firmware, and it may use support RIM format as Vincent introduced in Type 1 firmware. During the firmware boot, the system firmware can collect both the device firmware information and option ROM information. Here we can see that the device firmware reports three SPDM firmware measurements. The first one is type 0 immutable ROM. Its measurement is AAA. And the second one is a type 1 mutable firmware. Its measurement is BB. And the type 2, the third one is type 2 hardware configuration. The measurement is CCC. They all have a device context associated to describe what type of device this is. For example, the PCI context include the PCI vendor ID and device ID, and you can trace back to which vendor created this PCI card. A USB context includes the USB descriptor information, and you can know that what type of who created this USB. And the last entry is a PCI option ROM. It's measured at boot service driver, and it can know that information by the image device path. We have some reference example code on how to collect those measurements from the device. Although we do not have the real device on the market, we have some early test code to show how that works. First, the DMTF has a lib SPDM. It's a example implementation on the SPDM protocol. And the second is a device security package, which uses this libSPDM to communicate with the device in the EDK2 environment. So an EDK2 driver can use SPDM to talk to the device which implements the SPDM protocol and retrieve the device SPDM measurement from the device. And finally, the verifier gets the TPM PCR and event log, and it can get the corresponding device RIM. Then he can compare the digest of the option ROM and the digest of the firmware manifest in the event log entry. In this case, we show that every digest are same. For example, the firmware 1 digest matches the SPDM measurement. Firmware 2 matches the second one, and firmware 3 matches the third. However, in reality, there might be some case that some measurements are same, such as code, but some measurements are different, such as configuration. The difference may be caused by the desired modification by a value-add vendor. In that case, the change can be documented by the update RIM. The verifier has to find the update RIM to verify the change if the change is acceptable. Or the verifier can totally ignore the configuration difference based upon the verification policy. And see as Amy pointed out in the first entry, the appraisal can get the endorsement and can get the reference value, but he also get the appraisal policy from third place. This is very similar to the current BitLocker policy. The BitLocker can use PCI 7 as a policy or PCI 0, 2, or 4 as a policy. So in the future, we think We could have a generic verifier to compare those information, but based upon different appraisal policy. Currently, DMTF Standard Working Group defines the SPDM specification version 1.1 and 1.2. It is good enough to get the device measurement at the runtime. The TCG platform firmware profile spec already defines a simple way to pass the SPDM measurement with the TCG log in current spec. But now we're discussing a better or robust way to provide more information, such as device certificate chain to the verifier. So the verifier can have more information to know what device it is. At the same time, we're also discussing how to support device component RIM. Currently, IETF defined a various format like code suite, code mid, or code RIM to describe the software component as well as the hardware component. They are still under construction. So for the future item, we can still see two big challenges we have. For example, how we handle the hot block device. Do we need to measure or test the hot block device? If yes, then how do we notify the hot device added or removed? How we record the history to the verifier? Or do we need to record the history? The second big item is a runtime update. Do we need to measure or test the new firmware, new runtime firmware? Like in data center use case, people don't want to shut down the machine and reboot the whole system just because of firmware update. So a live patch mechanism is widely adopted today in the data center system. If that happens, a device firmware is updated at runtime. How we handle that case, and if we really want to measure that, how we notify the runtime firmware update to the verifier to give a chance that the verifier to perform some attestation again. Here's the summary and call for action. We know that the industry is preparing the supply chain identification, and today you can see the system firmware plays a role to report the firmware measurement information. System firmware as a leader tester it's a centralized place to collect all those information to report to the verifier. So we should get our firmware prepared. Here is a set of reference we conduct in our presentation, like a general supply chain guideline. There's some ISO guideline, NIST guideline from other country. There's a standard or specific guideline like NIST SP 800, the bias integrity measurement, or TCG published a set of specification to describe how we do that. In a PC client working group, TCG DICE working group defines the architecture, how to support the attestation for the small device. And IETF RATS working group defines some remote attestation architecture like concept RIM or concept suite. And finally, DMTF standard, published standard about the SPDM to enable the device to host the communication. Here's all our presentation. So we'll see if there are any questions.
Great. Thank you, Jaywin. The first question here is, what is PFR firmware?
So PFR stands for Platform Firmware Resilience. It's a capability in the Intel Xeon platforms to protect against attacks against the platform flash, say the low-level firmware. So it's essentially an example of a root of trust or a platform root of trust. So typically, a separate entity, maybe outside of your SoC, and in Intel's case of PFR, it's integrated into an FPGA that can detect and recover against malicious or other corruption of the motherboard SPI flash firmware. But again, it's an instance of a class of technology. So this sort of platform root of trust. There are other examples in the industry. Google's OpenTitan, Microsoft Cerberus, but PFR is specifically the Intel solution. So again, it's in our taxonomy of firmware. This would be like this, since it's device firmware, it's not running on the host CPU. It would be a class of Type 2 firmware.
What percentage of time to prepare firmware for a platform do you suppose is consumed with adding this support to a product?
It is likely not to be any additional time, as several of the tools that are currently available can be integrated into the BIOS build processes. There's some work that is happening in the PC client work group within TCG today around how you relate component RIMs into the regular platform RIM. And it's likely that we'll support a variety of models where OEMs can integrate the component RIMs into their platform base RIMs, like Jaewon showed in his example. It is also likely that we will support delivery of separate RIM payloads that are signed by the various entities in the supply chain without actually requiring any sort of integration. So it's really on it becomes an inventory management, inventorying system today, where you can, as part of your build process, generate the payload, and then the signing process for signing the artifacts, and then promoting them to whatever CDN or website that you would like. So I think really the work on this side is more building the infrastructure out. And once you get the infrastructure built, I don't think it adds any additional time.
Great, thank you. Will EDK2 support the SDM spec?
I would say definitely yes. The currently SPDM is I think 1.2 is in working progress state. I think EDK2 will definitely support that, and we already have some prototype to how to integrate SPDM in a security architecture driver. I think the only question we have is that currently we do not see too much real device that support SPDM protocol. So we have a few chance to test that support. That is the reason we just keep it as a POC directory. But in the future, once we can see a product on the market support SPDM, we will add this driver to EDK2 as an official one.
Okay, then the next question here is, given the firmware may contain software components from multiple different sources, is there an ability to identify the various component sources?
Yeah, yes, depending on the format of the RIM that is provided, it is possible to provide RIMs that will contain the source information for the various components. And that is one of the things that we are working to enable from a standards perspective, is how to ensure that the standards support a variety of different methods and use cases, such that if you do have a need to identify the individual components and the authorities that provided the RIMs for those, that is possible to do so.
Great, thank you. And with that, that's actually our last question for today. That being said, we are hosting a live interactive WebEx Q&A right following this webinar. So please feel free to move over to the WebEx now if you're interested in joining us and speaking with the presenters directly. So again, thank you, Jaywin, Amy, Vincent for presenting, and thank you everybody for joining. The slides will be available on the UEFI Forum website, and a recording of this will be made available on Bright Talks and the UEFI Forum YouTube channel. Thank you all so much.
Okay, thank you.
Thank you.
Thanks, everyone.